Section 14.3 talks about right triangles and trigonometric ratios. So this is something you guys are going to start relating a little bit more from the past into, but we have to tweak it just a little bit as we consider this. So if we think about our overall unit circle. So our unit circle had our radius of 1, and we talked about every point on here was the point cosine theta, sine theta. So basically, x, y was related to in here, and every single one had a hypotenuse then of 1, or that radius of 1. Well, what happens now is we start considering what happens to larger ones. So as we start extending this out, okay, we extend out into here, we start noticing that because it's a 1 here, it's really a scale factor being multiplied in here. So r cosine theta and then r sine theta. So what we start referencing overall is we start referencing sine cosine theta rather than just as an xy motion. We could be thinking about what happens when we have different hypotenuse. So what happens when we have this different in here? We have just an r motion going out with an x and a y up here. So if I kind of redraw this just a little bit down here so we can see it a little better, just in referencing in here, is we don't have anything going on. We just have our xy axis that's happening. So when I look at my points here, this is an x, this is a y, and r is going out here. So what we start talking about is we start talking about the simple fact that sine of theta equals y divided by r. Cosine of theta equals x divided by r. Tangent of theta, once again, is still going to be y divided by x. So I take y over r divided by x over r, simplify that. It's going to be y over x in the very end. And then also remember we have our reciprocal functions. So cosecant is the reciprocal of sine, so that is r over y. Secant of theta then would be the reciprocal of r over x, and then cotangent of theta is going to be x over y, or our cosine over sine function in here. Now, do realize all this really starts relating to our triangular motion. So remember, we have an x and then a y. Now, it's very imperative that you are referencing that x is first, y is second. One of the things we have to always realize on here within this. So if we start thinking about this motion, even different. Okay, so this was different. This is even more different, but still in the same direction. So just kind of putting some marks out here. These marks mean absolutely nothing. This is not my unit circle. Just kind of start and relate to the simple fact that instead of having our motion, okay, so let me switch to blue here. Instead of talking about we have to have this circle, we could start talking about, well, I'm going to go x out here, and then I'm going to go y up here, okay? And then I'm going to go so far out here. What we start talking about here is that theta, or our angle we start working with. So our angle goes to the x axis, okay? That way when we're referencing in here, we're seeing that our y is our opposite and our x is our adjacent, okay? So once again, if we were to think back, remember when we had that good old SOHCAHTOA, and I said, well, it's not going to work. Well, guess what? We can make it work. We can finagle it in here, but you have to make sure to draw everything carefully. Now, I will tell you, instead of using this, I think about everything up here as an x, y, r motion as we're going through it. That way, we make sure to have our correct angles and we're using everything correctly. Because I've seen so many times where people all of a sudden reference right here, and no, you can't. if I'm over here and I'm starting to do things. I can't reference this angle. I must look at this angle that's in here because everything has to be done to the x-axis. So this is something to be very careful with what we're going, but do realize that when we actually have a physical triangle, you know, let's say I drew this triangle right here, okay, and I have a right triangle, and I say here is theta, okay, we can relate this trigonometric ratio going on right here and not the unit circle portion of it to start thinking about what's happening overall. So if we start looking at some problems here, okay, looking at some problems overall, we're going to start by looking at problem number 10, okay? So on problem number 10, they give us a coordinate point, okay? They give us this point of -5, -2. And they ask us to find the values of our 6 trigonometric functions and standard position of this angle. So basically what we want to do is we want to figure out what are our ratios here. Well, how we start this is we start this by looking at this point itself. This is telling us we are going 5 to the left and down 2. Okay, so we have this point right here. This point is referenced in our third quadrant, once again going out so far. So if we look, we have a -5, we have a -2 for our motion that's on here. Now notice I'm in the habit of always referencing back to that x-axis. So that's why I wrote -5, then -2 down here rather than leaving that -2 over here. We need to figure out what is this length right here. So once again, this is a simple Pythagorean theorem. I can just call that r squared equals what would be a -5 squared plus a -2 squared. So that is 25 plus 4, so 29. Once again, equals r squared. So r equals the square root of 29. Okay, do realize r has to be a positive. It's talking about a radius that we're moving out here as we're going through. So it is not talking about a relationship in here. If r is ever a negative, and this does happen but more in vectors, that means we're going to have all this motion, but then instead of going that r distance, we go the opposite of that r distance. We go backwards on that line. So considering this, we have this now. Now it's asked us to find sine of our angle, cosine of our angle, tangent of our angle. And then we're to find cosecant of our angle, secant of our angle, cotangent of our angle. Now, our overall angle is this big angle right here, okay, as we're looking through and just calling it theta. Do realize how I wrote this out. I was very organized in my writing. Sine, cosine, tangent, and then my reciprocals are directly across because they're related so easily with this. So if we think about sine, sine is going to be our y motion over our r motion. So we see we have -2 over the square root of 29, which is -2 root 29 over 29. Because I'm using larger markers than I'm used to, I am running into a little room error in here. Cosine then would be that -5 over the square root of 29, which would be -5 root 29 over 29. Once again, rationalizing for that final answer. Tangent would be y over x, so that's -2 over -5, which is 2/5. Cosecant then is the reciprocal, and the reason why I wrote this original one down and just didn't write my rationalized answer is because when I take the reciprocal of this, I would have to rationalize again and then simplify. If I take the reciprocal of this, I'm already simplified. So I have negative square root 29 over 2. Here I have negative square root 29 over 5. And then here I have 5 over 2. So what we see is that we can easily, just by drawing out and seeing our x-y relationships and then figuring out that r distance, we can easily write out our trigonometric functions. If we look at number 12 gives a little story problem in here. It says you want to build a bicycle ramp that is 10 feet long and makes a 30-degree angle with the ground. Okay, so we have our ground right here. Going on, and hopefully that ground is fairly level. We're going to build a ramp. This ramp is going to be at a 30-degree angle. It's going to be 10 feet long. We're trying to figure out what is the height of this. Now this height should be a perpendicular to the ground in here. So if we notice, we have a nice simple triangle. If we have a triangle, we can relate back to our SOHCAHTOA. Once again, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So if we look at this, we have the hypotenuse and we're trying to find the opposite side of our angle. So if we're finding the opposite and hypotenuse, that relates to sine. So I state sine of 30 degrees equals x over 10. So that means x equals 10 times sine of 30 degrees. Okay? Once again, where x is our height. Okay? Sine of 30 degrees, if we think about this, sine of 30 degrees is 1/2. So we have 10 times 1/2, which means we are 5 feet from the ground. So if you have a board that's 10 feet long, you can do a 30-degree angle. That means you're going to be jumping off of 5 feet for that height within that. And basically, once we draw any triangle, so if we think about any triangle on here, once again, if we have our angle in reference here, this is our opposite, this would be adjacent, and this would be known as a hypotenuse. And that relates back to this that we've been taught so many times in the past and you were so familiar with until you came to our good old unit circle, because what happens if I want to build, 210 degrees? Well, that starts relating to a directional thing is what we're linking at today. One of the last problems we're going to look at, I believe I have one more after this one, is number 20 here. Okay, so on number 20, they give us some dimensions. So they give us some things to reference with. They state that we have triangle ABC. Angle C is a right angle. Okay. They now tell us, so number 20 here, here is A equals 5, B equals 6. They tell us to find the remaining sides and angles. Okay, so if we draw out triangle ABC, okay, so I will go A, B, C. Once again, C is our right angle. Side A is opposite of angle A, so this would be 5 here. This would be 6. We don't know what side C is, but remember, side C can be simply done by simplifying the Pythagorean theorem. The leg squared plus the leg squared equals a hypotenuse squared. Once again, given a right triangle in here. So C squared equals 25 plus 36. Excuse me. If I take 25 plus 36, we get 51. No, it's not 61. Got to carry the 1 over, so 61. And then we take the square root. So see, the square root of 61 would be 9 times 7 is 63, so it's not, so the square root of 61. There we go, nice and easily done here. So we see that side C equals the square root of 61. As we continue on here, now we got to figure out our other two angles. So this is the square root of 61. If we want to find angle A, tangent of A equals the opposite over adjacent. Now once again, I could use sine or cosine and relate it back to the square root of 61, but I always try to use the original dimensions that are given to us to solve, because that way, just in case we rounded here and didn't leave it as an exact answer, we could keep this answer to a better approximation, or not have the approximation have a more exact value. So A is going to equal the tangent inverse of 5, 6. So once again, we're going to put our calculator in here. We're going to take the tangent inverse of 5, 6. So if I take my tangent inverse of 5 divided by 6, or 5, 6, either way we do it, set that parenthesis in there, we see that we have 0.6940. This is radians. Go back there, it says round answer to the nearest tenths. So it doesn't necessarily specify we have to use degrees. But how many radians are in one triangle? So if you were to switch this over to our degrees, once again, just recalculating, you see you get 39.8. So angle A is 39.8 degrees. Well, we could do the same thing to find angle B, but do realize if we have a triangle and we are in Euclidean geometry, so that means that the sum of our interior angles is going to equal 180 degrees. Take 90 away, that means these two angles have to be complementary to each other. So because these angles are complementary to each other, angle B is going to equal 90 degrees minus 39.8 degrees. So we see that angle B equals 50.2 degrees. Now it's always appreciative that when we come up here, we label and we write our answers as best as possible so we know what's going on. Do realize that capital letters are distinguished for the angles, lowercase letters are distinguished for the side lengths. So if you don't want to put the actual angle in front, you make sure you use the capital letter here for what that angle would be. The last problem of the day would be relating to number 28. Okay, so if I look at number 28 here, 28 says cosine of theta equals 1/5. It tells us to sketch a right triangle with theta as a measure of one acute angle, find the other trigonometric ratios, okay? So I can just look even before I do anything, go secant of theta equals 5, because once again it's a reciprocal. But we still want to find sine theta, tangent theta. Once again, this would relate to cosecant and then cotangent of theta. Relating to everything in here, what we would do is we would take our triangle itself, we would reference theta, and thinking about what's going on here, cosine would be adjacent over hypotenuse. So this would be 1, this would be 5. So what we would do is we would take our 5 squared equals 1 squared plus x squared. So 25 equals 1 plus x squared equals 24. So x equals 2 root 6. So we go 2 root 6 right here. Now notice I did not draw my right triangle to be perfect on here, but it's just a measurement that we're looking at. So if you remember, sine is going to be opposite over 2 root 6 over 5 over hypotenuse. Tangent is going to be opposite over adjacent, or just 2 root 6. Cosecant then, now we're going to do the reciprocal, so we have 5 over 2 root 6, which would be 5 root 6 over 12. And then here, if we take the reciprocal, this would be 1 over 2 root 6, which is root 6 over 12. So once again, we see that we get our other 5 trigonometric ratios. Once again, we draw our triangle out, and we use the simple fact that given that this was off of a right triangle, we have our hypotenuse length here, and we have our adjacent to the angle side length right here.